Good morning, everyone. Thank you for joining us this Friday morning for the Team Research Forum. We are going to ask everyone to mute their microphones. I am going to go ahead and mute everyone's microphones upon entry, but I really appreciate if you can just quickly make sure your microphone is muted. We just want to keep the background noise to a minimum. I also recommend you keep the video off because it just helps with the quality of the video that you're going to be seeing. All these sessions are recorded, just a quick reminder. And we're going to maybe give people 1 more minute to join us, and then we'll get started.
Lucy, are you going to show kind of the agenda for today?
I do not have a slide with the agenda.
Okay. Well, I think Janine comes after me.
Right.
Is that right? Okay, that's all I need to know.
Okay, it's 10:32, so we are going to get started. Thank you again if you just joined us. This is our second Team Research Forum of 2024. It's going to be focused on space exploration. We're really excited to have you all here. I am just going to remind you again to keep your microphones muted, and I recommend that you keep your video off too. I'm going to pass it on to our Associate Vice Chancellor for Research, Professor Christina Davis, who is going to be our host for today. As always, please post your questions in the chat box, and I'll be monitoring that for anything that comes up. Christina.
Absolutely. Well, I am thrilled to do this introduction today because Steve Robinson is one of my favorite colleagues, and he is in my home department, which is mechanical and aerospace engineering. Now, Steve is actually not new to the campus. He is an alumnus from our program. He actually graduated with his bachelor's degree here before going on to get his master's and PhD at Stanford, and then launched into a 36-year career at NASA. During that time, you know, he was so accomplished, as we can all imagine. He was an astronaut among other research duty stations that he had. And as an astronaut, he flew 4 shuttle missions, and he spent 48 days in space. Time on the International Space Station, and then like 20 hours of spacewalks. So just a tremendous amount of subject matter knowledge that's helping to drive his work here since he rejoined us as a faculty member. So as a faculty member, he actually has also been incredibly accomplished. He was our former department chair for some time. He's also the current director for the Center for Spaceflight Research. And then he's had many other honors that he's had here, like the Distinguished Engineering Alumni Medal. He was the College of Engineering Outstanding Faculty Teaching Awardee one year. He was the UC Davis Graduate Advisor and Mentoring Award. So just so accomplished. But I think one of the things that I like to say, and I didn't know this completely until today, is that Steve is the only person I know who can play both the banjo and the tuba. And that's a pretty good accomplishment. So Steve, I'm going to turn it over to you.
You could have left off the first 90% of that intro, but it was a very nice introduction, Christina. Thanks so much. Christina Davis has been a friend and a mentor to me before I even got here. When I was thinking about leaving NASA and coming to the UC Davis, now that I've been here for 12 years, she is even more so a friend and a mentor. So it's great to have you and everybody else. Thanks for making time in your morning to learn about spaceflight research and teaching at UC Davis. And I want to just say right now is one of the big reasons we have this is to invite you to be in contact with us to share our interest in spaceflight engineering and research. There may be collaborations possible, certainly communication. So this is a community building event here today. And so we're very excited to kick it off. So I'll share my screen here, a couple of slides to show you. Alrighty. That is a picture of the Space Shuttle Endeavour on its second to the last flight, taken from the International Space Station. Endeavour is now the one down in Los Angeles. It might I was on that spacecraft when the picture was taken. My journey there started at UC Davis, like Christina said. I got here as a freshman in 1973, a young, skinny, hairy freshman, very excited about studying aeronautical engineering. And I had learned that UC Davis actually had an airport and a Department of Aeronautical and Mechanical Engineering, and that did it for me. So that is why I came the first time, and it's also why I came the second time in 2012. So here, 36 years later, I think, getting ready to launch on my fourth mission. And so 13 years ago from right now, I was in space, actually, with my crew. And working with a crew of people we were helping to build the space station. Working with an amazing bunch of people was certainly the best part of that job. I was an astronaut for 17 years and flew 4 times and also trained as a cosmonaut in Russia. Those were the days of the space shuttle. And it was an amazing feat of all kinds of engineering, especially human systems integration. And that's something we study, kind of our focal point for spaceflight research, at least in the Center for Spaceflight Research that you'll hear about today, is the human part is an essential element of how we call ourselves unique here at UC Davis for space research. Launching is the act of imparting a huge amount of energy to the spacecraft, but especially the humans inside. That is inherently dangerous. And making that, I don't want to call it safe. If you wanted to be safe, you would stay home. But making that as safe as can be is so much of what spaceflight research and engineering and testing is all about. Christina mentioned spacewalks. You are surrounded, covered, completely enclosed in products of engineering. And this is a picture of me attached by my feet to the Canadarm. My whole family's from Canada. My parents were immigrants from Canada, and I was born in Sacramento about a year after they got to the U.S. Actually, on one of the missions, ended up doing an emergency spacewalk to work on the heat shield of the shuttle Discovery. Fortunately, that worked out very well. And took my very first selfie ever from space to show the tiles on the belly of Discovery. And you could see Discovery today in the National Air and Space Museum in Washington, D.C. at Dulles Airport. Let's talk a little bit about this. UC Davis Center for Spaceflight Research. First of all, it does exist. It's always in the process of being born, I would say, but it's a great time to kind of talk about what our vision is, which is enabling human exploration, utilization of space. And the core part of what we think about in this center is that bolded part: predict the behavior of complex engineering systems integrated with human beings who have complex bodies and complex brains. So this is truly a transdisciplinary effort, and it stands on the shoulders of lots of students, a very diverse team. I'll just show you one org chart. I won't go too much into that. Basically, we have the Center for Spaceflight Research is a national collective, as we see it. It's kind of an umbrella that includes many things, including 3 NASA research institutes. One is the Space Technology Research Institute, Habitats Optimized for Missions or Exploration, or HOME. This is a very large research effort. It's been going for 5 years, has 7 different universities, 75 researchers, and we are the lead for that. As well as another research center sponsored by NASA and working for NASA. All of these are, which is one where we're studying human capabilities for autonomous missions. In other words, human autonomous, humans not linked to mission control as much as they are today. And then finally, operational performance and its neural basis for lunar and Mars missions is our third NASA center that we're part of. And we have currently 4 different professors, all of whom you will hear from today. So my lab is the Human Robotics Vehicle Integration Performance Lab. We'll also hear from Professor Kong, Professor Whittle, and Professor Joshi. We are, the center is largely based off campus, actually, in East Davis, right next to the Center for Mind and Brain, which is exciting for us. The fields of study are quite broad, given our charter. As I say, human systems integration and habitats for both the microgravity and partial gravity environments on surfaces. To operate these facilities and to design them and learn about them as safely as we can, we have to understand human learning, teaming, and human performance. This leads to life support systems, which we have to think about human health and physiology in space. You'll hear from Dr. Whittle about quite a bit about that today. Spacecraft design, autonomous and AI-enabled many subsystems, but especially robotics. UC Davis is a great place to study and develop robotic-aided plant growth in space and lunar surface infrastructure development. And bottom line is spaceflight safety and risk awareness and analysis. Tell you a little bit about this Home Institute. It is for semi-autonomous human habitats in deep space, and the reason it has to be semi-autonomous is because this class of spacecraft, which does not exist yet, and NASA asked us, this was a competitive selection of a team to work for NASA to look into the type of spacecraft that could be enabled by autonomous systems, learning systems, that can hold a crew only for a couple of months out of every couple of years. So you have to have a fully capable and redundant life support system that actually is dormant for most of the time. We've never had a spacecraft like that. So what using modern current technology can we really think about when we think about the spacecraft? And like many other things in a control systems type of point of view, the spacecraft has to have the ability to sense its state, make decisions, and take actions. As I said, there's 7 universities involved with this, with industry affiliates of Blue Origin, Terra Space, and Collins also. And so it's UC Davis, CU Boulder, Carnegie Mellon, Georgia Tech, Howard University, Texas A&M, and University of Southern California that are involved in this. Great, big, very active group. The technical research thrusts are the vehicle functional design. We're not designing vehicles, but we are designing the required functions. The spacecraft has to have self-awareness, be constantly updating its state estimation, and then predicting it for the near future. Human autonomy teaming is essential. Spacecraft have to be able to take care of itself when the humans are not there. And underlying all of this is what we call our central nervous system, which is a very advanced concept for digital twin that has the ability to model and predict the near-term future states. Coming right back down into the 1 or 2 rooms at the Center for Spaceflight Research is the HRVIP lab. Our mission is to safely extend human capability in extreme and hazardous environments, like space, through advances in combinations of engineering, human autonomous systems, human cognitive capability, learning, behavior, and the neurosciences. This is exciting because engineering students, or students sometimes who are not actually engineering majors, get a chance to integrate all of these different things into their research projects. And often in engineering, we're kind of guilty of not mentioning humans. And here we're graduating students who are well aware of the role that humans can and should play in engineering systems. The vision for this lab is, as it is for the center, certainly transdisciplinary between engineering, human systems integration, safety, applied cognitive psychology, neuroscience, and various biomedical and human health interests. Which means we have a lot of research areas. The big lab, we've just before Christmas, we had 18 graduate students, I think 14 undergrads or so. We try to match, have the same number of undergrads as graduate students. That works very well for us and gives some great opportunities. So the main areas, and I'm going to go through all these different things, but it's humans and systems integration, human spacecraft, humans and aeronautics, and humans and robotics and autonomous systems. And of course, these are kind of mixed together. We're not a very siloed organization because Mother Nature isn't very siloed either. I'll give you 2 examples of some big projects out of about 15 that are going on in the lab. One is we are developing a class of inspection satellites where large spacecraft, high-value spacecraft, occasionally have to be have some sort of damage or failure on the outside of the spacecraft. And right now, the way to inspect that is mostly by sending out a couple of astronauts on a very risky spacewalk. And that's probably not the best way to do that. So we are developing a class of very small spacecraft that are cheap enough to be disposable. Nothing like that exists. And as far as I know, we're the only people even working on it anymore. Go to the next slide. Whoops. This has led us to developing some really fascinating technologies, such as the ability for a spacecraft to orient itself, to turn itself in space without touching anything, using a technology that is well known called reaction wheels. But what nobody has done is used hard disk drives as reaction wheels. So reaction wheels, instead of costing between maybe $5,000 and $20,000, and there's 3 or 4 of them on a spacecraft, they cost about $100. So it's disruptive. It's a game changer for the small satellite business. To the right is a kind of a staged cold gas propulsion system that we're testing for small satellites. And then another example of big projects we have going on here, it's been going on for quite some time, is a space ambulance concept, where if somebody is at death's door on a space station and has to be brought home, this is basically a space plane. And coming home on a capsule is actually a very violent ride. And somebody who is seriously injured is not going to be in better shape after such a violent ride. And so this is a space plane and can land on a runway next to medical facilities. We've got a full-scale mock-up of the pressurized version, and we're working with UC Davis Medical Emergency Medicine Department, and also starting to work with Baylor College of Space Medicine, and also Harvard. And there's an Aggie in space, and just like I was 13 years ago. With that, I'd like to introduce you to. I guess we're going to do a Q&A at the end, right? So we'll just move on. I'd like to introduce you to the next speaker, who is Janine Moses, and she is the manager of the HRVIP lab. She's here right now with us to give the perspective of the graduate student. I think we often hear the faculty members start, but we know who really does the work and who does the thinking. And so here's Janine to give that perspective.
Thank you, Professor Robinson. Hi, everyone. I'm Janine Moses. Let me share my screen. Let's see. Okay. So as Professor Robinson said, I'm a graduate student in the HRVIP lab under the Center for Spaceflight Research, and I'm also the lab manager. I am a master's student, hopefully graduating this June, knock on wood, and I'm going to tell you a little bit about what life is like in the lab from a graduate student's perspective. This presentation is basically completely crowdsourced, so I just asked all my friends in lab to send me pictures of all the fun stuff they've been doing to highlight for you what collaboration opportunities we have, and again, just what it's like to work in the mechanical and aerospace engineering department on space exploration. So first, I want to point out and name our diversity, equity, inclusion, and accessibility efforts and our outreach efforts. I think in STEM spaces, this is often left as an afterthought. And I want to emphasize that we try to not have it as an afterthought in our lab and continuously talk about it and name our areas for improvement. We are currently working on a web page on our website about our DEIA efforts and some specific concrete actions we're taking to meet our DEIA goals. We also have an outreach program where members from our lab and other folks around Davis will go into elementary and middle schools and get kids excited about STEM, especially in the years where kids are often discouraged from pursuing STEM, especially girls. So here we have some examples of learning about earthquakes with Jell-O and marshmallows and toothpicks, and then learning about how craters are made on the moon using flowers and dropping rocks onto a tray of flour. So anyway, I'm gonna talk a little bit now about highlighting some ways our different projects in the lab and our different graduate and undergraduate students get to collaborate with people from really all over the university. Like I said, this presentation is all pictures. So on the top left, we have an example where you would never really think that we would need to interact or talk with all the theater kids, but we had a really cool opportunity to actually work with the theater department to help mimic using their spotlights, the really harsh lighting conditions that you would see in outer space to help train a computer vision system that would be used for the inspection CubeSat that Professor Robinson mentioned. The next picture below, as part of the Home Institute that Professor Robinson also mentioned, one of the research areas is working on an environmental control life support system. So basically getting rid of all the carbon dioxide that humans are exhaling on a deep space habitat. And one of our students who recently graduated a year ago worked with the Department of Viticulture and Enology to create her test bed for the CO2 removal test. We also have another version of that test bed, the center picture, where we work with the chemical engineering department. And we have several graduate students who have backgrounds in chemical engineering who then came over to aerospace, to the dark side, to work on the space exploration aspect. On the top right, also as part of the Home Institute, we have folks, an undergrad who's working on building a deep space habitat analog, and we're working with the California Lighting Technology Center, which is actually just down the road from us in East Davis, to help improve and determine what the best lighting conditions are for astronauts when they're in deep space without the natural sunshine you would get on a nice, beautiful day. The bottom left is a little bit of my own work. I'm working on spacecraft waste heat rejection, so how to keep electronics cool when you're in space, using technology that's been used on spacesuits in the past, but has never been scaled down to a really small spacecraft version. And I actually got to work with the CMGI, the Center for Molecular and Genomic Imaging, to get some 3D images and work on post-processing those images of the hardware that is used in that thermal cooling system. And then the lower right is you wouldn't know it by looking at it, but it's actually the beginnings of a astronaut-powered space laundry machine to reduce the amount of clothing that needs to be basically thrown out or brought back to Earth on a deep space mission. And Andy, the grad student on the left, has worked with the chemistry, material science, and the textiles departments. So as you can see here, we've gotten to reach our hands into so many different disciplines, even outside of the College of Engineering. We also collaborate, as Professor Robbins mentioned, with institutions outside of UC Davis. So the Space Ambulance Summit, he already talked about, but we've gotten to work with folks involved with wilderness medicine, military medicine, and the UC Davis Med Center Emergency Department. On the bottom left, we have some of our lab members participated in a design of a glider for a high altitude balloon data recovery system. So getting a hard drive with all of the data from a high altitude balloon down to the ground in a specified location. And you can see they're practicing with a 10-foot drop before the real drop. This top middle picture shows some more work at NASA Johnson Space Center on the reaction wheel technology using hard disk drives, or HDDs. And some of our students, both grad and undergrad, got to fly out to Johnson Space Center in Houston and work with the engineers there to help integrate some of our technology into their CubeSat. On the top right, we have another collaboration with Johnson Space Center's HERA, which stands for Human Exploration Research Analog, where they put humans in a room essentially for 45 days and they do various research to mimic being on a deep space mission for an extended period. And part of the one of the institutes, the HCAM Institute that Professor Robinson mentioned, we got to implement this research project and do human subject testing on the folks in HERA to look at enhanced procedures for astronauts to do tasks for the first time in a more efficient and accurate way. The bottom right shows me, that's me right there, holding our HRVIP sign, and a few other, Daniela and a few other HRVIP alum working again at Johnson Space Center in the Neutral Buoyancy Lab to create a helmet-mounted display for crew members or astronauts to use to train during their spacewalk training underwater. That was really cool for me because I got to scuba dive with some of my childhood heroes in the NBL, the Neutral Buoyancy Lab, while we were testing out some UC Davis hardware on these astronauts. Another really amazing opportunity that our lab got to participate in is zero-G flights. So a zero-G flight is when an airplane, like basically an airliner you would fly on, flies in a parabolic motion, and at the very top part of the parabola, you get about 15 to 30 seconds of weightlessness, and it's a great way to test out technology before putting it all the way in outer space. So we had two big projects that went on several zero-G flights. The first is called Changes, which stands for something. I'm blanking right now, but it's essentially how to help people not get motion sick when you have a very dynamic gravitational environment. If you're going from Earth to outer space, where there's 0G, to the moon where there's 1/6 G, or Mars where there's 1/3 of Earth's gravity, we want you to have a good experience without getting motion sick. And this is a non-pharmaceutical countermeasure to that. And let's see if this video plays. This shows the way that we tested out this non-pharmaceutical countermeasure. And you can see we're having some fun floating in the background while our human subject, one of our lab members, Rachel, is testing out the hardware. And then on the right side, we have a tech demo of the inspection CubeSat reaction wheels, as we mentioned. And you can see there's little markers that look like VR codes on each of the sides of these because we use a computer vision system to help determine the attitude and how the CubeSat was changing when it was floating in zero-G in the airplane, to verify that this technology was really working the way we expected it to. And here's just some pictures of some of our fun parabolas that we did. And we have, I think, about 15 members in our lab who across 4 zero-G flights or 5 zero-G flights all got to participate and help out on these research projects. So that was a really great opportunity for all of us. And this this flag you see here is the one that Professor Robinson flew in space about 13 years ago. And that was fun to take that up with us. The last thing I want to mention is all the internship experiences that we have collectively as a lab. We have a lot at NASA. So we've got Karen May over here at Johnson Space Center, and which is in Houston, as I mentioned. Jonathan, an undergrad, was working at P&G this summer. I am an intern at NASA Goddard Space Flight Center working on some thermal control for telescopes that launch into orbit. We have Monica, who got to wear the spacesuit that Collins Aerospace is testing, Shannon at SpaceX, Andy getting potty trained at Johnson Space Center on the astronaut toilet for the next Orion capsule for the Artemis program. Katie and Keldon are both interns at Armstrong Flight Center doing flight operations work. So there's Katie in the cockpit of a DC-10, and then Daniela and a few other folks, Monica as well, have worked at Blue Origin, working on their life support systems there. And then Sean, when he was an undergrad, interned at Langley. So this is just a small snapshot of the range of experiences that we bring to the lab and the connections that we have where we can, work, collaborate with our former mentors and people who we network with and meet at all of our various internships. We also, try to attend as many conferences as we can. I know I am almost at time. So we have our undergrads present at the URC every year. And it's a great opportunity for them to practice their presentation skills and folks to learn about what we do in the lab and what's it like to be an undergraduate student in the lab. We have a number of projects all related to human factors and humans in space. Go to the Human Research Program Conference every year. And then this is a gathering from the Home Institute, which Professor Robinson mentioned. This bottom picture here is Lily, one of our undergrads, presenting. She's a McNair Scholar, so presenting at the McNair Scholars Program Conference over last summer. And then the upper right is Angel, who is part of the UC NSF camp. And he actually just presented this poster at the symposium last weekend, and he won the Thermo Fisher Scientific Award for his poster and for his presentation. And then here I am with some other lab mates presenting at the ICES International Conference on Environmental Systems, which is everything space related, essentially. My last slide is just what is life like as a lab member. As I'm sure you all know, it is hard to balance. It is hard to balance everything, but we have weekly seminars going on where we bring folks from outside to talk about what they're doing and how it relates to space exploration. So if anyone here is interested in giving a seminar about their work, we would be happy to host you. We are also currently working on developing an art residency program where we are going to work with the design and studio art departments at UC Davis and have members from those departments come in and create art based off of inspiration from our lab and from the Center for Spaceflight Research. So we're really excited about that. And we also participate in sports as a lab. We had a pretty good losing streak, if I remember correctly, and we had a lot of fun. And we also oftentimes TA and act as guest lecturers for the Space Vehicle Design course. And then on the bottom right, This shows celebrating Professor Robinson's birthday after our HRVIP band played a song and we sing a song for him. So we also have band practice and other fun activities like that. So we try to stay sane amidst all of the research and activities going on. And I believe that is all I have. So I think questions are saved till the end. And next is Dr. Rebecca Librand. I hope I'm pronouncing that correctly, who will be talking about soils on and off the Earth.
Great, thank you so much for the introduction, Janine, and for an excellent presentation. Hi, everyone. My name is Rebecca Librand. I'm an associate professor in the Department of Land, Air, and Water Resources, and I am thrilled for the opportunity to be here today. So thank you for the invitation to talk about applications of soil science research on Earth and beyond. A bit about me. I am a soil scientist. I love soil, and I love getting to look at soil whenever and wherever I can. My work has spanned from thinking about soluble salts in Death Valley to permafrost landscapes in Alaska, checking out soils in Japan, as well as looking at soil development and carbon persistence across a number of forested landscapes from Arizona to the coastal temperate rainforest in Alaska, as well as up in British Columbia. And finally, I have found myself back in desert environments, thinking about cold desert ecosystems as Mars analog sites in Iceland. Before I jump in, I just want to acknowledge so many people and colleagues and students who've made this work possible, especially thinking about our mineral weathering mesh bag project that I'll be talking about today that we've deployed most recently in Iceland, as well as an amazing team of collaborators at Goddard, as well as the Johnson Space Center. And I'm also so excited to be connecting with more folks at UC Davis. And I hope you don't mind, Rich, but I went ahead and included some photos of you as well as our team getting to connect. And I'm just really excited to collaborate moving forward. So you'll be hearing from Dr. Whittle here in a couple presentations. So overall, as a soil scientist, our lab has been really focused on microscale weathering features and thinking about microscale controls on soil formation. And over, we kept seeing connections pointing towards the need to bridge soil science with the planetary and space sciences. And for that reason, one of the main questions driving our work is thinking about how can soil science advance the search for life and habitable environments on Mars and beyond, from distinguishing biosignatures to better utilizing terrestrial analogs on Earth for planetary exploration. I could give an entire lecture on the importance of soils in space, and I actually do in my extraterrestrial soils class, but I wanted to just briefly touch on a few reasons that thinking about soils in space exploration is absolutely critical. One is the search for life and thinking about what types of environments are habitable or potentially could be habitable for life, or when certain types of minerals are discovered on other planetary surfaces. The example I have here was the discovery of the Martian blueberries, understanding how those minerals may have formed and whether it could be driven from a biological formation mechanism or through some kind of water-rock interaction. Space agriculture is another really important realm where soils come into play, whether we think about plant growth and growing crops, using materials from another planetary surface, or even what types of substrates would be most effective for plant growth during space exploration. And then finally, one example of in situ resource utilization would be actually understanding how to use the materials that are on the moon or on Mars to construct buildings or other types of important structures on these surfaces. And for these reasons and many more, NASA has invested energy and time and resources into training astronauts on how to sample rocks and soils and sediments. And this is an example of Jaws. She's an astronaut who's actually on the International Space Station right now, but she was part of the expedition that our team was able to join NASA on a few years ago in Iceland. And Iceland overall is a really important training ground, both as a lunar analog as well as a Mars analog. And it's been used as a training ground since the Apollo missions. So there have been astronauts going to Iceland for training testing vehicles and other types of instrumentation for several decades now. So I'm going to focus on 3 research areas. I'll just briefly talk about each one as potential areas of collaboration. If you find yourself intrigued or interested in any of these, please reach out to our team. The first is thinking about soluble salts in terrestrial analogs or on Mars. And this work started thinking about perchlorate and nitrate salt distribution in Death Valley, and has expanded to analyzing archive samples from the Atacama Desert, as well as Antarctica and nitrate deposits in China. So these are all different types of terrestrial analogs where we were looking at the co-occurrence of perchlorate and nitrate salts. And you may be wondering why this is important or applicable, and that's because perchlorate has been discovered on Mars. And perchlorate salts are both viewed as a resource and a hazard. A resource because it's a strong oxidant, so it could be used as a potential propellant for surface operations on Mars. It's also a hazard. Perchlorate interferes with iodide uptake in the human thyroid, so astronauts inhaling this through dust or even ingesting perchlorate through food or water sources could be problematic from a human health standpoint. So for that reason, NASA is really interested about why on Mars perchlorate presents percent level differences on some of the landscapes within very, very small distances. Within a meter or less, there may be percent levels of perchlorate in one type of soil and then a different, much lower concentration of perchlorate in another. And so this would actually be helpful to understand the controls on this and why. So this is an area that we would be really interested in working more in. The second research area is thinking about terrestrial analogs and how soils form in terrestrial or Mars analogs. And the example that I'm presenting here is for Iceland. And so Iceland is often referred to as the land of fire and ice. And so you can see the glacier stretching across the background here and the volcanic landscape in the foreground and this beautiful rainbow. Don't be fooled though, this was actually our wettest, coldest, and windiest experience during our NASA expedition. But the soils were worth it. These were just amazing and stunning soils, especially observing evidence for soil development at depth and thinking about the different processes that led to the windblown deposition of the darker materials you see on the surface and then the redder materials that you see in the subsurface. And so for those reasons, we're really interested in understanding how these soils form, especially the preliminary stages of weathering. So in addition to collecting these soils to take a closer look at our lab, we also put out fresh ground basalt rock as well as pre-characterized mineral chips. And we are in the process of securing funding to be able to go back to retrieve these samples and to test some of the prototypes that we deployed in Iceland to better understand the biological inputs on mineral weathering and soil formation versus just water rock interactions. And one example of how we plan to compare this with what's going on Mars is that the Mars 2020 mission with the Perseverance rover is actually able to collect pretty detailed elemental data. And we are taking a similar approach using electron microprobe to better understand the elemental distribution as well as the degree of alteration of these different types of basalts that we collected at these Mars analog sites in Iceland. So the third research area that we're just starting to get into, and we're really excited about this, is thinking about growing food on Mars. And to conduct this, this is more so a controlled laboratory experiment where we collected fresh volcanic rock deposits in collaboration with a NASA volcanologist, again in Iceland. And we've been analyzing the differences in these rock deposits. And we noticed that these basalt substrates actually have different chemical and physical arrangements that we think will impact how plants or food products can grow in these different types of substrates. And so this is an example of a preliminary scan conducted by our collaborator, Dr. Doug Rowan, over in the biomedical engineering program, thinking about how roots may change their branching patterns or growth patterns as they grow through these different types of basalts. And we're really excited that the Space Rock Garden experiment was funded by NASA under the Space Biology Plant Studies program. And I'm about to show you some examples of our amazing controlled Mars simulation chambers. And I wanted to give a shout out to Dr. Dragos Saharescu. He's an assistant project scientist with our lab. And overall, the focus and objective of this experiment is to understand how basalt substrates impact plant growth in environments relevant for human exploration. And so as I finish up here, I just wanted to show a few images about how incredible it was to see the space chambers go from a design to Dragos making them a reality. So he just finished constructing these chambers most recently. And these chambers will be able to control for atmospheric composition. So we'll be able to simulate Mars atmospheric conditions, as well as perform some radiation treatments. And so this is the last step here, which will be testing out the different basalts, as well as how plant growth does within these types of simulation chambers. So I know we're saving questions until the end, but I do want to briefly just acknowledge funding from NASA, as well as our NASA collaborators and members of the lab. Thank you for your attention. I'm excited to talk and to collaborate. And up next is going to be Dr. Khan, who is going to talk with you about robotics and deep space exploration.
Thanks for the introduction, Rebecca, and then thanks for the amazing talk. So my name is Zhaodan Kang. I'm associate professor in the Department of Mechanical and Aerospace Engineering, the same as Christina, Steve, and Janine. And then I'm also part of the Center for Spaceflight Research, and also I'm also affiliated with the Center for Neuroengineering and Medicine. So my lab is called the Cyber Human Physical System Lab. It's one of the 4 labs of the Center for Spaceflight Research. And then my lab mainly focuses on to engineer and understand assured autonomy and then collaborative autonomy. And then the method we use includes control theory, optimization, machine learning, and formal methods. And then we have been using this method to solve a wide range of problems, including the modeling and then modulation of brain activities, the application of UAVs or drones for disaster response, and then finally human autonomy teaming, which is something that I'm going to talk a little bit more today. So essentially, the first question you may ask is why we care about human autonomy teaming in the context of space. So what you're seeing here is a picture of the kind of NASA Mission Control Center. So currently, the astronaut on board the International Space Station, they're supported by the ground crew here 24/7 and almost in real time. And this mode of support won't be kind of available for future deep space missions, mainly due to communication delay. And then if you think about it, if in the future you want to send humans to Mars, and then there is this delay, communication delay, it takes about 4 to 24 minutes for radio signal to travel between Earth and Mars. And then because of this and some other constraints, such as the communication bandwidth, and then if you want to, for future space missions, you want this mission to be successful, and then these humans must be work with either AI agents or robots to complete these missions. And therefore, the effective collaboration and communication between the AI, the autonomous systems, and then the robot become very important. And then my collaborator and I are mainly currently investigating 2 research questions. And the first research question that is very interesting is related to human state sensing and assessment. So basically, we're interested in how can intelligent machines measure and assess human state in real time. And the second research question we are interested in is human-machine communication. So basically, how can intelligent machines to communicate their kind of internal representations or processes or predictions to humans in an understandable manner? So essentially, we are thinking about the bidirectional communication. So first of all, the machine has to understand the human, and secondly, humans must make themselves understandable by the human. Okay? And then what I'm going to do, I'm going to spend a little bit of time to talk about each of these projects. The first project is related to human state sensing and assessment, and this is in collaboration with Professor Sanjay Joshi, I believe is the next speaker, and then collaborated at CU Boulder, and then the Air Force Research Lab. And the work we are working with are this amazing group of postdocs and students on this particular project. And then the kind of the state that we are focusing on right now is trust, specifically human trust in autonomous system. So why trust is important in space and in a lot of other domains is because of these two kind of scenarios. The first scenario is what we call under trust. So basically, the autonomous system can perform quite well, but somehow the human does not trust the autonomous system. And the other one is more dangerous. So this is what we call overtrust. Basically, the autonomous system cannot perform well, but somehow the human trusts it. Okay. So what we want is eventually the trust a human has in autonomous system must fit essentially the trustworthiness of the robot or autonomous systems. And this process we call calibrated trust. Okay, and calibrated trust can really help us to guide against misuse, and disuse can lead to enhanced safety. And in order for autonomous system to be able to calibrate the trust of the human, and then the autonomous system must be, first of all, to figure out what is the trust of the human. Okay, so that's essentially the kind of the question we want to ask ourselves right now. And what we have done is we have designed this task, as you can see here on this screen, on the kind of like upper right. So this task is inspired by a deep space mission, and then you can think about here a human, either a remote operator or onboard crew member is working together with the robot, let's say, to fix a leak. Okay, and sometimes the robot will make a mistake, and the robot may drop a cube or place you can think about the cube as a tool, and then or place the tool at the wrong place. Okay, and then in the meantime, we also constantly ask the humans to or occasionally to ask humans to read their trust, to tell us, so basically at this particular instance, so what is your trust of this particular robot? Okay, you can grade it from 0 to 1. 0 means you complete distrust the robot, and 1 means that you completely trust the robot. And in the meantime, we collected a lots of biosignals from the humans, from the human subject, including FNIR, EEG, ECG, EDA, IRSP, and then gaze tracking data. So essentially what we want to do here is we want to be able to use this signal that we can collect from the wearable sensors in order to decode or to infer or to estimate human trust without even asking the humans about their trust. Okay. And then for those of you who are familiar with machine learning, and this is a very standard machine learning task, right? So you have the input, which are the biosignals, and you have the output, which are the ground truths, which are basically the human trust. Okay? So what we've done here is slightly smarter than just using just use some very standard machine learning algorithm. So what we've done there is we incorporate the kind of some series from dynamic system theory and also neuroscience, network science. And then by incorporating these two kind of series, and then we have found out that we're able to dramatically improve the performance of our decoder. So what you're seeing here is basically the errors in the kind of trust prediction and trust inference, and then we can show that our model can outperform almost all the state-of-art method there. And not only that, and our model can also allow us to generate this type of picture. So essentially, this picture shows the kind of like you can think about which area or what frequency band and which area is more important in the context of inferring or predicting trust. And I believe that this can help us to understand the neuro scientific kind of mechanism that's related to the establishment and then the maintenance of trust of humans. And something that we're working on right now include, the kind of the we call it closed loop cognitive state estimation and control. So now we're able to infer human trust, and then in order to calibrate human trust, we must be able to find a way to affect human trust. Okay, for instance, you can do that by apologize or by explain, so basically the string, and then that can essentially to calibrate the human trust in real time. And another research direction that we are currently undertaking, which involved almost all the speakers today, is related to biomarker discovery. And essentially in future deep space missions, and due to all these space flight hazards, including, for instance, space radiation, and then altered gravity, and then the onboard members, they may experience cognitive or behavioral health decrements. And then we must have a way to detect and to even predict the onset of this decrement. And then we believe some of the models, methods we develop here can be used for this particular, to identify these biomarkers. And I believe Professor Rich Guido is going to talk a little bit more related to this particular topic. So the second project, for the sake of time, I'm probably just going to go over this rather quickly, is related to human-machine communication. And this is in collaboration with Steve and also Professor James Napley at the CU Boulder. And we are working with our 3 students here. And the first thing that we did is we conduct a survey with students and researchers, and also NASA engineers, and also flight and mission controllers. So in this survey, we asked them to imagine, okay, if you are working, let's say, with a robot or working AI to fix a leak in, let's say, deep space habitat, and what type of explanation that you want to get from the autonomous system. And these are the kind of the response that we have got. And essentially, kind of, if you look at the first 2 type of kind of preferred explanations, the first one is, why is that? And the second one is, what if it fails? Okay. And for those of you who are familiar with causality, and then this basically, essentially, these human subjects, they prefer causal explanations and counterfactual explanations. And these actually fit quite well with what we found in social science regarding human communication and the human explanation. And then if you think about this in the ladder of causalities, this basically the ladder causality has 3 type of ladders or layers. The lowest one is association. So this is basically what we learn in statistics. And then the second one is intervention. Okay, this is related to causality. And the last one is counterfactual. So essentially, it seems a human prefers the kind of either causal or counterfactual explanations. Okay, and this type of causality sometimes we call actual causality, and this has actually been used in the field of law, to, for instance, to assign blames and the responsibilities. Okay, and what we have done is we have developed an algorithm which can basically to provide these actual causal explanations in the context of anomaly response. Okay, and then we have developed this algorithm, and then we have also tested it in a testbed. And then this testbed, by the way, is called, interestingly, called STEVE, stands for Simulation Testbed for Exploration Vehicle, ECLSS. ECLSS stands for Environment Control and Life Support System. And what we have done here is we inject particular fault, and we see whether our algorithm is able to identify this particular fault. And we have shown that our algorithm can not only exactly to pinpoint the time and also the location of the fault, and it can also provide explanation to the humans in a way that is acceptable and understandable. And something that we are kind of working on right now, so basically, if you think about what we have done, is currently the AI can provide explanation to the human. And then what we're doing right now is we are trying to enable the AI to also to take the human's feedback and suggestions into consideration, and together they can solve, for instance, the anomaly response problem together. And this is what we call human AI collaborative anomaly response, and then human AI collaborative decision making. And then that's the end of my talk. Thanks for your attention. And then if you want to learn more about my lab, please visit my lab's website. And then our next speaker, I believe, is Professor Sanjay Joshi, and then I think he's going to talk a little bit more about human autonomy teaming.
Yes, hi everyone. Thanks, Professor Kong. Let me start sharing my screen here. There we go. Yeah, thank you, everyone. This is really exciting to see all this different work going on, and to be able to speak to you a little bit. My name is Sanjay Joshi. I'm a professor in mechanical and aerospace engineering, and I run a lab on campus called the Robotics Autonomous Systems and Controls Lab. which most people at UC Davis know as the Rascal Lab. So if you hear Rascal Lab, that's probably us. We do a number of different things in the lab. We do control systems, we do autonomous robotics, we do human-computer interfaces, and we do neuroengineering, which is the field of bringing together our knowledge of neuroscience and engineering together, which I'll talk a little bit more about also. So as you've heard from many of the faculty and students who spoke before, in our lab, we also are very highly interdisciplinary. We have students from many different graduate groups, and we have many students from mechanical and aerospace engineering, certainly, but many different kinds of engineering, including fields outside of neuroengineering, in the computer sciences and neuroscience and psychology and the healthcare fields. So this, I think, is one of the things that distinguishes UC Davis in general is our goals of combining different disciplines, both at the lab level, at the center level, and really at the university as a whole. So I think that's what makes UC Davis a really exciting place to do work. We work in many different applications. We work in medicine, we work in biology, but we also do a lot of work in space, and this forum is focused on space. So we'll talk more about some of the space technology projects that we have had and are doing currently. And we'll talk some more about human-machine cooperation. I myself came to UC Davis after a career at NASA. I had about 7 years of working at NASA, both as a graduate student and after my graduate work, doing a lot of work on how to control spacecraft and how to control robots and looking at different space observatories. This is a picture of Deep Space One, which is a mission to a comet and an asteroid, which tested a bunch of different things. So as you, again, a common theme is that many of us have had some experience in the aerospace sciences before we came to UC Davis. We're training students who are right now working at NASA and throughout the aerospace industries. And when they graduate, we have just a wide network of alumni that are working in all kinds of areas in the aerospace industry. But what do students do in our lab? We do a lot of different things. One of the things that we do is we figure out how to control spacecraft. So one of the most important things you can do when you have a spacecraft is to make sure that it's pointing in the right direction. So if we're going to go all the way to different planets or asteroids or comets, once we get there, it would be great if the camera was actually pointing in the right direction. And once we collected the information, if the information got back to Earth, so we're pointing the antennas in the right direction. That's called attitude control. So this was a project that we did with the Naval Postgraduate School, in which one of our students was looking at new ways to control spacecraft that may be vibrating at the same time. There's a whole new class of spacecraft that are called CubeSats, that are really small spacecraft. They can fit in basically a 10 by 10 by 10 centimeter cube. You can also put those cubes together, kind of like Lego blocks. And so we've done some work on how to control those kinds of spacecraft and how you should put them together in ways that would help specific missions. And this is a collaboration we have with Cornell University, in which one of the PhD students in my lab developed some control theory about how to control these kinds of CubeSats in different configurations, and then was able to test out his control algorithms on a test bed that Cornell University had built. Another interesting area is how robots will work together in space and maybe on the surface of Mars even. So you might think of robots that are in formation, and there's a lot of very interesting mathematical control theory called adaptive control theory that can be used to think about those things. Here's a picture of two robots that are following each other. So there's an interesting research area of how to get robots to follow other robots, how to get robots to follow astronauts, maybe on the surface of Mars, even how to get robots to follow doctors as they're moving around in a hospital. So these are two robots that were roaming around our hallways in Boehner Hall and thinking about what is the best way for a follower robot to keep up with a leader robot. And as you can imagine, one of the difficult things about following the following problem, really following anyone or anything, is that the leader can do all sorts of very unexpected things. So we all know this when maybe we have two friends that are we're trying to follow when we're trying to follow another car on the freeway, or so the leader may be able to do may take a sudden sharp right turn down a hallway, and those kinds of things are very difficult still to get robots to be able to take it to contend with. One of the big things that we do in the lab is human-computer interfaces. And so I mentioned before that we combine our knowledge of neuroscience and physiology with robotics and controls with all kinds of devices that could help people. We started working a long time ago with trying to help people in the disability community with all kinds of different interfaces if they may have some mobility problems that are difficult for them. We work on prosthetics, for instance, how we may develop control systems to control these more and more advanced prosthetics that we get. So this is more in the field of biomedical engineering, but it leads to some very interesting questions. So one of the questions that it's led to is for us to think about in space, if we had an astronaut doing a spacewalk, wouldn't it be great if they had some additional help to do that spacewalk with an assistive robot? So this astronaut may be using their two hands to fix something, but at the same time, wouldn't it be amazing if they could also control a third assistive arm that could also help out in the task at the same exact time? So this is a field called supernumerary robotics, and the really cool thing about this research area is that we have a really tightly knit group of researchers, including Professor Robinson and Professor Schofield from the Mechanical Engineering Department, and also Professor Millers and Professor Joyner, who are neuroscientists, all working in a tightly developing team. We do this because it's very interesting to study. First of all, it would be amazing if we could build control systems to control robots and have them be useful. But as people would learn to maybe use these kind of assistive robots, their brains and their bodies are also changing. So from a neuroscience perspective, it's very interesting to study how people's brains and bodies change as they use these kinds of assistive robotics. I'll mention we already had 2 PhD students who graduated from this project and are both working at NASA. I kind of talked a little bit about this, but here's some of the kinds of test beds that we developed for supernumerary robots. We have Harsha, a graduate student here, who's controlling a game on the computer screen using his 2 hands, but he's also using his leg to control that robot you see in the back. To collaboratively do something on that computer screen. We're building some really cool test beds that allow us to control robots while we're using our hands at the same time, and we're monitoring everything using brain signal monitoring. We're giving different kinds of feedback. So we have, I think, some very, very unique test beds in this area that are going to help us to study all kinds of different things about about robotics and how people behave. Professor Kong already mentioned this, but trust is always an important issue. If you're going to ask a robot to do something, what happens if they do it? What happens if they don't do it? How should that affect the teaming? So I won't go too much into that because Professor Kong has already mentioned that. Just let me finally end off by saying that, yeah, part of what important things that we do is bring all of this ideas and excitement to the next generation. This is a summer camp that we run with a number of different faculty involved that teaches middle school students about robotics and even neuroscience and many different kinds of technologies. So with that, let me end and say thank you. And there's a lot of different resources at UC Davis that you can look into that cover all of these things. Talked about RASCL, of course, the UC Davis Center for Spaceflight Research. We have a whole center on campus that's dedicated to combining neuroscience with different engineering devices. That's the UC Davis Center for Neuroengineering and Medicine. And I encourage you to look at that center and also the NASA Habitats Optimized for Missions of Exploration Institute, which you've heard about also. So with that, I thank you, and I'll stop sharing my screen here. And I'm going to introduce the next speaker, who is Professor Rich Whittle. And Professor Whittle joined the Mechanical and Aerospace Engineering Department very recently and has a very a background in a wide variety of areas, and he studies human spaceflight. So with that, I'll give it to Rich.
Hi, everyone. Hi, hopefully you can hear me. Just going back to, there we are. Sorry, it's yeah, really hard to follow all these incredible speakers. I've just got here. I turned up here in July, so I've been here about 6 months. But I'll do my best to follow. And what I want to do today is talk a little bit about some of the research that I've done, and also a little bit of teaching, because hopefully there's some people here that are interested in collaboration, and you might not know what NASA is looking for, what NASA wants to do in the human health sphere. So I'm going to show you where you can find that information as well. So a little bit of a start. As you can tell by the accent, I'm British. Into my undergrad in the UK. I then joined the British Army. I was a British Army officer for about 15 years. Finished working in industry for a little bit. Came and did a master's in the UK. Did a PhD in Texas A&M, and then started here in July. And what I do is bioastronautics. And so for people that haven't heard that term, what bioastronautics is the combination of engineering, medicine, science, and operations that enable humans to survive in space. So pretty much in keeping with the theme that everyone's been talking about today, this is a whole variety of disciplines. This is physiology, psychology, cognitive science, human factors, lots and lots of different disciplines of aerospace, of engineering, aerospace, structural, electrical, operations management, risk management, medical devices. So again, you're seeing all of this potential for collaboration here. Because no one person is an expert in all of these things. And that's the great thing about coming to UC Davis. So when we talk about human spaceflight, and really this is the NASA view now, there are the hazards are categorized into 5 main areas. So space radiation, isolation and confinement, the distance from Earth, gravity or the lack thereof. So that's microgravity or partial gravity, and then hostile closed environments. And you get some of these things on Earth, say in submarines. You might get hostile closed environments or isolation confinement, but that combination of these hazards is unique to spaceflight. We then define from hazards, we talk about risks, and NASA has got about a master set of about 30 risks. So this one's the risk of spaceflight associated neuroocular syndrome, which is astronauts losing vision in space. And from those hazards, on the left here, you can see distance from Earth and altered gravity, and you can see a network of causality that's taking you through this risk all the way up to, on the right-hand side, you can see loss of mission objectives and loss of mission. Okay, so and then long-term health outcomes down on the bottom right. So you can see this this really connected causal network of risks. So these are kind of what they are, and a brief name of them. I say there's about 30 of them. So things like the behavioral medicine risk, the risk of bone fracture, risk of decreased muscle mass, non-ionizing radiation. But where can you find out more about these? So I think that'd be a useful thing to share with you guys. It's all public data. So the Human Research Roadmap, and the link up there, if you search Human Research Roadmap, you'll find it. They've got a website. You can go into this website and you can explore the roadmap. You can look down, you click on explore the roadmap, you can see all of these different risks. So this is all of those different 29 risks from 2 slides ago. And if you click on one of these, it's going to take you to a lot more detail on that risk. So you can find an evidence report of why NASA think this is a risk, a kind of risk profile where they think they can accept the risk. So this one is risk of injury due to EVA operations, and they can accept it for low Earth orbit, but they need to mitigate it for Mars missions. And then in that risk, you've got all of the tasks. So you can see all of the specific things that that NASA are really interested in and really concerned with focusing on. And then how they're planning to close those. So this is a great opportunity to look for areas of potential collaboration, look for areas that need funding, look for open gaps in the human research program. And that kind of brings us on to what I've done and what I've done and what I'm planning on doing. So my lab is we do a combined experimental and computational approach to tackle some of these problems. So this was an experiment we were looking at potential causes of spaceflight associated neuroocular syndrome. So I had human subjects and I was tilting them on an inversion table and measuring their intraocular pressure, so poking them in the eye. And simultaneously while we were doing that, we were also constructing a mathematical model of the eye and modeling the changes in changing the gravitational vector. So you can see on the right here the agreement between our experimental data and our mathematical models. Similar things were, looking at the jugular vein response to altered gravity. The astronauts have had a problem with altered flow patterns in the jugular veins, which can lead to, in one case, has led to a venous thrombosis, and there's a concern that could be an elevated risk profile, particularly as we're expanding access to space, getting more people, commercial astronauts that maybe don't have the same medical risk background that government astronauts do. So looking at the jugular vein response to altered gravity, and again, this was a combined experimental and computational model. So we had a computational model of the human cardiovascular system and the upper body and the neck circulation. Looking at the response to lower body negative pressure and the multivariate response. I do a lot of Bayesian statistics. So if you're ever after a statistician, this is something that I do as well. A lot of stats. Looking at those multivariate responses. Again, looking back at ocular perfusion pressure and SANS, and looking at the relationship between spaceflight associated neuroocular syndrome and potential terrestrial conditions that might have the same symptoms and the same pathoetiology. We looked at sleep and stress in analog astronauts. I know Janine talked about HERA, and this is a different analog. This is the Mars Desert Research Station. So we looked at a couple of crews there and how their stress and mood disturbance decreased over the course of the mission. We looked at VR as well. So looking at virtual reality for exercise. Obviously, there's huge terrestrial applications here, but can we gamify exercise to encourage people to want to do it and encourage astronauts to want to do the 2 hours of exercise they have to do per day on the ISS, just to maintain fitness. I've done some work on EVA safety systems. I'm a systems engineer by background, so I really like to bring in some of that systems engineering as well as the physiology. I'm not quite sure whether I'm a physiologist or an engineer more now, and I'm in the mechanical and aerospace engineering department, but I'm really keen to keep that transdisciplinary research going. And then something I'm just starting to look at now is really predictive metabolics for EVA. So you're on a spacewalk. How can we predict the best routes, the best escape routes, based on our metabolics that we're using? And then what happens if spacesuit starts going wrong and we start getting elevated levels of carbon dioxide? How does that affect our metabolic planning, our cognitive planning, and how does that affect our mission plan? So that's everything, and I think I'm the last speaker, so I left this question slide on there, and hopefully I finished enough time to leave some time now for questions. Yeah, it's 10 minutes. So I'd like to, I guess, maybe pass back to Annalise here and Christina, and they can perhaps open the floor to questions.
Christina, do you want to moderate, or do you want me to just start asking questions? We can just start asking. There's a question for Janine already in the chat box. Janine, could you talk a little more about your work on the helmet-mounted display and the feedback the EVA astronauts gave?
Yeah, so the helmet-mounted display, or HMD, as we call it, the whole point is, or of this project, was a technology demonstration to see what is the, immediate, like, low, short timeline, relatively cheap way we can help astronauts train to get a better sense of themselves and their physical exertion as they're training for an EVA in the neutral buoyancy lab, using a helmet-mounted display so that they can be better equipped during a real EVA to not expend as much energy, kind of like what Dr. Riddle was just talking about. So the focus of this was more of a tech demo, but specifically some of the feedback that the crew members gave was a lot about like how much information is enough but not too much when I'm engaged in this task that might be taking up a lot of my like physical and mental energy. So for example, in the NBL, you could measure, we have the capability to measure an astronaut's metabolic rate by how heavy they're breathing, essentially. And if their metabolic rate was getting too high, you would have some sort of like flashing on the screen indicating, here's your metabolic rate, like here's the number. If it turns red or orange, you're getting close to your limit in terms of like your physical exertion for a 6-hour EVA. So a lot of feedback we got was about how to convey the right amount of information with it not being too much. And then we also had a few other non-medical or non-biofeedback related bits of information, such as really short EVA procedures, like if you're unscrewing a series of fasteners on some external part of the International Space Station, maybe what order do you have to unscrew those bolts in, or how many turns do you have to use, do you have to unscrew them for? So really basic things like that were also found to be helpful because the crew members could quickly look at their helmet-mounted display and without having to ask the mission control, communications folks, can you say that again? How many turns? And similar to like how much time has elapsed on an EVA, they really liked having that information for like how many more hours am I going to be out here. Yeah, that's the short version. I could send you a conference paper, Toby, if you'd like to learn more.
More questions from our audience. I'm really interested. I have a very like brief soils background, but I'm very interested, Rebecca, in like how are these like analog locations selected, and what are like some other analog locations that are being looked at right now for soils?
Definitely. So the analog locations, there's no perfect analog, right, for Mars or for thinking about lunar materials, but you basically choose based on what you want to explore. So Iceland is a very important analog if you're interested in basalt rock, especially in cold desert ecosystems. But another pair of analogs that are very frequently used and compared are I mentioned it briefly, is the Atacama Desert, the hyper-arid core in the Atacama Desert, along with the dry, the desert valleys in Antarctica. And these landscapes are really important from the salt deposition standpoint. So these are stable enough that nitrates and even perchlorates over millions of years have been coming down as deposition and accumulating. So if you're interested in understanding soluble salt distribution, then you would probably set up some type of analog study in Atacama, or even thinking about Antarctica. So you basically, select the analogs based on what topic you're most interested in exploring.
Thank you, Rebecca. I'm feeling kind of like I want to go and dig some trenches with you somewhere. Right.
All right. Yeah, you're always welcome.
You take volunteers.
We love having people in the field.
Any more questions from the audience?
And again, folks, if you're interested in talking to any of us about any of these topics, please don't hold back. Send us an email or send an email to Ana Lucia, and she'll put us in touch. Again, community building is what we're trying to do here, and so you matter to us, no matter what your interests are.
Absolutely. There's a question from Courtney Merson. Can you say more about your outreach to young people in the area? Who wants to take that? I'm just going to ask our speakers to be concise because we have some more questions coming in. Outreach to young people in the area. Janine, I know like that the HRVP VIP Lab has a program, and I know Sanjay also has a program. You want to say something, Janine, about your outreach program?
Yeah, can I actually? Yeah. So our outreach program is meant to show students the possibilities of STEM in elementary and middle school. Let me turn my video. So we're not, forcing them to go into STEM, but showing here's people who you can connect with more, who maybe look like you, and some of the things that we do. So we'll oftentimes have a show and tell for the younger, grades, or have like some of the activities I showed earlier in my presentation, just to get kids excited about it. It is hard because it's not our priority. Our priority is being students and researchers, but we do try once or twice a quarter to go into classrooms in Woodland and Sacramento to really like engage with our local community. And I can put a link to our outreach website in the chat.
Sanjay, I think you spoke also to around outreach to local community. I think you're muted. We can't hear you.
Thank you. We're running a summer camp associated with the Supernumerary Robotics Project, actually, in which, since that's a combination of neuroscience and robotics, we have a 3-day experience for middle school students who learn a combination of how computers work, how robots work, a little bit even about neuroscience, and then they get to come to campus and see some of the research projects from a number of different professors. So yeah, we're really excited about that. Thank you.
We have another question from Dragos from Rebecca's lab. How much priority does NASA human spaceflight program put on growing food or recycle food waste for long duration missions? That's a question for Steve.
Great question, and the answer is quite a bit of priority on the growing of food, recycling food waste. There's kind of sort of energetics of a spacecraft is a really interesting process, and this goes into it. Are the calories stored in the chemistry of food waste, can they be used in some way? So there are some calculations being done on that, but on growing food, there's quite a large effort at Kennedy Space Center. In fact, we're collaborating with them. We just met with them on Monday. Here in this lab, we have a fairly new project that has a great acronym, most important part, robotically enhanced precision agriculture in space. And if you know your French, you know what that means. And but the idea is, here at UC Davis, we have a large spectrum of plant biology experts, like you, and we also have quite a bit of expertise in robotics. And one of our study areas in robotics research is manipulation of flexible objects, like plants. And so working with the NASA folks and the folks here at UC Davis, all of whom are experts in plant growth, but we imagine this: you're going to a space station that has been in space for several months or maybe a year or two, and you arrive and there's already fresh produce that has been grown, harvested, and stored while you were in transit. That's what we imagine, and so this requires a lot of robotic capability that doesn't exist yet. So we're definitely collaborating with NASA on that, and I think we're going to visit the plant science, plant growth facility at NASA in Florida here next month.
I also just want to mention we have researchers like Professor Karen McDonald in chemical engineering, who is part of a NASA-funded project around food for space. And we're always happy to make more connections with other researchers. I think we have time for one more question. We're like 1 minute over time, but is there, do people have maybe one more question? Going once, going twice. Okay. If you are, oh, Daniel Sebrat, Professor Sebrat has a question. Go ahead, sorry.
Yeah, I'm just wondering about exactly what the best way is to start making the connections. So the work that I do is kind of quite orthogonal to everything that's been discussed here, but it would definitely be good to try to set those connections up. And I'm wondering what's the best way to do that. Okay, thanks.
Send me an email. Putting it in the chat here.
Perfect.
I'd love to hear about your orthogonal research. Hey, and everybody, thanks so much for your time today to listen to us. Next time, we hope to be listening to you, and especially thanks to Ana Lucia, whose idea was this whole thing. And see, there's one more picture, a question in the chat. We may be out of time, but you might want to copy that one, Rich.
Yeah, Julianne, I've just seen your question. Just take a screenshot of it. I will find your email. I'll shoot you an email. We can set up time to chat about that.
Well, thank you for joining us today. It's 12:02. Hope you have a wonderful Friday. If you're interested in connecting with this group or with any other of the speakers of the Team Research Forum, or you have an idea for a Team Research Forum, or you are looking for a collaborator and just having a hard time finding someone on campus, please reach out to my team. We're at strategicinitiatives@ucdavis.edu, and we are happy to help you make a connection. Have a wonderful weekend, and we'll see you in a few weeks for another Team Research Forum. Thank you for joining us.
Cool. Thanks, everyone.
Thanks.
Thank you. Thank you.